Welcome to another episode of 3-Minute Videos with Daniel. Today we will now discuss something really out of this world. Yes, out of this world. And I mean it. Imagine yourself in a void. Yes, a void. Now put a point in it. What do you see? A point. Now put another point. This time join a line connecting these 2 points. Not very interesting, so let's move on. Get another point. Take 2 more lines connecting to that point and then wrap it with bubble wrap. I don't know. Anyway, you proceed with a triangle, which you extend it becomes a plane. Now, you put another random point, making sure it doesn't lie inside the bubble wrap or inside the edges of the triangle. This time, you will have what is called a tetrahedron, and it is the very start of our polyhedral studies. Let's draw a tetrahedron. The reason why I pointed this tetrahedron out is because it is the smallest possible polyhedron ever made. Now, what could be more complicated than a tetrahedron? Well, we know about pyramids, right? So you could imagine a tetrahedron as a triangular pyramid. You can imagine a square pyramid. And this has 5 faces, and this is a pentahedron. Besides, it has 8 edges, 1, 2, 3, 4, 5, 6, 7, 8, and it has 5 faces, which means that if you replace each of the faces with vertices and each of the vertices with faces and all the edges rotated around, then you get what is called the dual of the polyhedron. And strangely enough, there's another polyhedron which is also a pentahedron. You might know it very well. It's a triangular prism or a wedge. Sorry, I'm still drawing. So there you have it. It's a triangular prism. And so far we can build these with regular polygons. Now, let's move on to hexahedra with 6 faces. Hexahedron number 1, the one that you might be most familiar with, seen in dice. Well, no prizes for guessing this one. A cube. Yep, a cube, nothing special about it. Now the next one, the Pentagonal Pyramid. Yep, nothing special, it's just an extension of what we've seen earlier with the triangle and square. Now, the next one, which is the triangular dipyramid. Whoa, this is starting to get interesting right now. And since a triangular dipyramid is basically just stack 2 tetrahedrons on top of each other, which is really interesting when you think about it. You might think it looks like an octahedron, the platonic octahedron of course, but it isn't, because there's 3 edges here in this vertex and 4 vertex here. That's why it doesn't make it an octahedron, which is a platonic solid, which means that in this wants to be this little triangular dipyramid is an octahedron wannabe. This should have 4 edges crossing this point. This is starting to get interesting. Now, imagine if you chop the cube in half. Yep, and I mean it, chop the cube in half. You get what I would call a semi-cube. Yes, this is half a cube, and if you turn one around, you can piece the 2 together and it'll become a cube. And this is the most simplest polyhedron that you can make without using regular polygons. What if you chop off 2 corners of a tetrahedron? This shape is actually called the pentagonal wedge, or as I like to call it, the pentagonal almost prism. Because it looks like a prism, right? Because it looks like a prism, because this was lifted upwards, this could be a prism. Now, probably, let's move on to another polyhedron. It's the mix-up pyramid. So basically, it's just a pentagonal base, and then you have square, triangle, and then you have square again. The triangle, these 2 triangles cross, then the square here, and then this triangle. It's a very strange polyhedron, I tell you, and you want to make it, go! And you can't make this with regular polygons. I haven't tried it before, but let me tell you something strange about this polyhedron. This polyhedron has the same number of vertices, faces, and edges as the semi-cube, and the one that we're going to see is the pentagonal wedge, shares the same number of faces, edges, and vertices with the cube. They're similar in some ways, but they're that creepy kind of similar. Now time to meet the 7th hexahedron, the final one, and probably the craziest, the Tetragonal Anti-Wedge. Hold on, I'm still trying to draw a Tetragonal Anti-Wedge. One crazy thing about this polyhedron is that one, it is self-dual, meaning in that when we do the dual procedure, you'll still get the exact same polyhedron. And what's even crazier is that there are left-handed and right-handed versions of this polyhedron, which means if you put a left-handed version on front of the mirror, you will have a right-handed version. And this is chirality. And that's why I call the Tetragonal Anti-Wedge the first chirohedron. Now, we have 7 of these here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can we arrange them in a triangle? The answer is yes. Then we put the tetrahedron on top because the tetrahedron is the start of it all. Then you put the square pyramid here and then the trigonal prism. Then what we're going to do is that we're going to count the edges for each of them. The cube has 12, the pentagonal prism has 10, the triangular dipyramid has 9, the semi-cube has 11, the pentagonal wedge also has 12, the strange pyramid, I call it the pentapyramid, the pentastranger pyramid, it has 11 edges just like the semi-cube, and this tetragonal anti-wedge has 9. There, now we have 1, 10 face, 10 vertices. So where do we put it? We are going to put it right here in the middle of the triangle. So pentagonal pyramid. Now we put the cube and the pentagonal wedge and on top of it, and then we'll put 9 edges. So we have the trigonal anti-wedge and the triangular dipyramid. Then we put the 11 vertices, the 11 edges one, and the semi-cube, and the strange pyramid. I prefer calling it the pyramid. No. That's a daft name for the pyramid. You know, yeah, really. So here's a neat way of arranging these 10 polyhedra in a triangle. Now, how about we add the heptahedra, 7 faces, and the octahedra, 8 faces. Before we go on, let me just say that the trigonal anti-wedge is sometimes shown in a taco form. And what I mean by taco form, which means you have these 4 triangles in the middle of the taco and the 2 tetragons carefully doing the shell of the taco. You get it? So this is the taco form and it's not counted because it's topologically the same to the tetragonal anti-wedge form. You get it? So let's add these up. So we have 1 tetrahedron, 2 pentahedron, 7 hexahedron. After that it goes really fast. 34 heptahedra, and finally 257 octahedra. Why 257? You don't know, because it's just 8 to the power 8 over 3 plus 1. Still laughing at it. So we have 2 8s, and then the platonic octahedron has 3-sided polygons as its faces, and the 1 here is to represent the unity. And you know why the 1 is here? Well, if you add these up, and 301, which is 300, a triangular number at once. So that means you have a gigantic triangle, 24 polyhedra on each side, and you have this 1 here. Probably that explains why the 1 is here. Anyway, these are just coincidences related to 257. And just a side note, 34 is a Fibonacci number, 7 is a Lucas number, and 257 is a Fermat prime. So we got 3 special numbers in this sequence of counting polyhedra. Anyway, I hope you enjoy this polyhedra, and if you're so artsy as to make some of your own, go and you can send your nets to me so that I can make them for my audiences, and obviously I'll credit any of you who does this what I call the tetractys of tetrahedra, pentahedra, and hexahedra. Goodbye!